Hello all. Today's class we discuss about the multiplexer cascading facilities. First of all, it is noted that the cascading of multiplexer are designed in a various way. Number one is using algebraic method. Number two is truth table method. Number three is implementation, and number four is one of the most important, is known as Shannon theorem or known as multiplexer tree. So what are the algebraic technique? Multiplexer cascading means we design higher order multiplexer using lower order multiplexer, like a design 8:1 multiplexer using 4:1 multiplexer, where in an 8:1 multiplexer the control input is ABC, this is a LSB and this is MSB, and for 2:1 multiplexer 4:1 the control inputs are AB, where MSB and LSB are A and B respectively. And say consider this is a function of an 8:1 multiplexer output. This is min term 0, A bar, B bar, C bar into I0. These are data input. This data input 1, data input 2, and so on up to 7 input. That is 0 to 7, 8 inputs are available, data inputs are available. And for 4:1 we know that these output equation of this. So these output equation of 4:1 multiplexer, these output equation of 8:1 multiplexer. Okay, now say for example, now this is our problem, one mathematical problem. So design this logic of 8:1 using 4:1 using algebraic method. So the method name is algebraic method. So what we will do, first of all we separate A and B, because we represent this equation in the form of this equation, so now first of all we separate A bar, B bar. So A bar, B bar with C bar. That means if we represent this equation in this form, that means this is A bar, B bar into I0. So this is apply in I0. Next A bar, B. A bar, B means there is a no A bar, B. That means I1 equal to 1, 0. Then we select AB, that is C bar. That means it I for I2, and for A B bar there is a C plus C bar, that is 1. So this is apply in I3. So I0, this is a 4:1 multiplexer where A and B are the two control input, these are output, this is a control input, and this is 4R data input, and this is enable line which is grounded. This is active low enable, that's why it is grounded, that is 0 volt. And what is the status of I0? I0 means C bar. That means here we connect one signal and gets complemented it, and from this line are connected to I0, that is C bar. Next I1 equal to 0, that is grounded. The next this extremely sorry, this is I2 and this I3, because this is AB. Okay, so I2 equals to 1, that is plus VC, and I3 equal to, yeah, right, that means I3 equal to, what is the status of I3? C bar. That means connected from here. So this is an algebraic method by which we design 8:1 multiplexer output using 4:1. Now next is a truth table method. So by using truth table method, here you also design 8:1 marks using 4:1. So this is a truth table of 8:1 marks of the control input, and we partition this table. And look here, there are 2 to 4:1. One is 0 0 0 1 1 0 1 1, another is 0 0 0 1 1 0 1 1. But here when A equal to 0, this multiplexer is selected, and when A equal to 1, this multiplexer 2 is selected. So here we use 2 multiplexer, I0, I1, I2, I3. Outputs are connected to the OR gate for the composite, because multiplexer have only one output. This is an output, this is a control signal of B and C of the 4:1. This is B and C. Now A MSB, which is connected directly to this enable line, but via this NOT gate it is connected to the second multiplexer. Now what is the logic? Now logic is that when A equal to 0, this multiplex is selected because the output equal to 1, and if this equal to 1, this enable is deactivated. So a when a equal to 0, and if we apply here 0 0, then this logic is selected. That means this is I0, and then 0 1, then this, then 1 1 0, then 1 1, and when a equal to 1, now this multiplexer is deactivated, but this multiplexer is activated because the output line, the logic equal to 0. So now if we apply here 0 0, so the logic is 1 0 0, that is this input I4, and then for 0 1 I5, for 1 0, that is this for I6 and I7, and the outputs, two outputs are connected to the OR gate for the one common signal to get only one output. So this is a equivalent block of 8:1 multiplexer by using 2 4:1. Okay, so this is the method by using truth table method. Next one is called implementation table. This is an 8:1 multiplexer logic. Say this is an algebraic equation. Say consider this and soft from represented by 4:1 multiplexer. So what we will do, we design first an implementation table. Implementation table is that when a bar equal to 0, then these inputs are 0 1 2 3, and when a equal to 1, then these inputs are 4 5 6 7. Now here which min terms are present, 0 1 2 3, sorry 4 5 7, these min terms are mapped here by using circled, this circled. So 0 4 1 5, this 1 5 2 and 7. So when two variables are marked, then the outcomes is 1, and this is for 1. Here only 1 marked, and the associated signal is, yes, right, a bar. Here 7 marked, the associated signal is a. And one thing should be remembered, that if any one of these is not get marked, then the output logic is, yes, right, logic 0. Okay, so now here we apply B and C control signal. These are an output for, and these are 4:1 marks. These are enable line which is get low 0 volt, and our logic is first I0 I1 gets logic 1 connected, then here we apply one signal A, and this is A bar, A complement, this is A complement, and A complement is connected to both I2 and I3 as per the design. Sorry, A bar is connected here and A is connected to I3 lines. Okay, so this is the method of implementation table. Now we talk about very important, our today's lecture is very important for this theory, multiplexer Shannon theorem. One thing should be remembered, using multiplexer theory or Shannon theorem, we represent multiplexer equation in a Shannon theorem formula. So for 2:1, here I just example, this is an output equation of 2:1 multiplexer. So for 2:1, there is only one control input, and 4:1 there is a two control input. Now if we see that this equation is represent in a term, say for example this f of a is basically the output equation equal to a bar I0 plus a I1. So this equation is basically first a bar, that means this is represented by the form of the equation, that is a bar, and so this is a bar f0 plus a into f1. So that's why here f0 and f1. How we represent this equation? Because a bar means here function a bar means the 0 symbol is present, and a equal to means the 1 symbol is present. So that's why here two inputs are f0 and f1 respectively. It is very clear for the 4:1 that the 4:1, the function of a b means there are two control input a b. Now first we'll take the common term is a bar. So what is the status? 0, yes, right. And now we take a. So what is the status? 1b. Because we design 4:1 multiplexer using 2:1, that's why we represent this equation in a 2:2 form. Because in a 2:1 multiplexer we see that there are two terms. This is a first term and this is a second term. Okay. Now again individual term represent this f of 0b. So b bar is common, that is f of 0 0. B is common 0 1. For this term f of 1b, that is 1 0, that is is 1 1. So now if we design, so this is first consider the level 1, this is level 2. So for level 1 this is the control input A, because here A is common, and the two inputs are f of 0b and f of 1b. Now f of 0b, this is equivalent to I0 and this is equivalent to I1, because a bar I0 or a bar AI1 is a output equation of output equation of two-station multiplexer. And now again this f of 0b is breaking into two parts, f of 00, f of 01. So here we connected one multiplexer which control input equal to b. Okay, so now here we apply 00 and 01, 00 and 01, and for 1b this is 10 and 11 for I2 and I3. So this is a design process. This is a multiplexer and tree. This is look like a multiplexer tree to implement 4:1 multiplexer using 2:1 multiplexer. Okay, so that's why it is known as Shannon theorem. This is known as the Shannon theorem, the Shannon formula, by using the multiplexer output are separated equivalent to 2:1 multiplexer. Student, it is your homework, that is design this logic 8:1 logic using 2:1. So first of all I separate here A common, here A bar and A, and getting up these two, and you please remember from the Shannon theorem this part is again break in two parts. Okay, so this is a level 2 and there is also one level that is called the level 3. So this is your home task, to construct this 8:1 multiplexer logic using 2:1 multiplexer using, yeah, right, what is the algorithm? Shannon theorem. Yes, right.